Welcome to the technical session organized by Nigeria Society of Engineers, Manchester branch, titled Managing Failures in Energy Systems. Are we masters or slaves of data? Our guest speaker today is one of our own, and we are very proud of that. Engineer Dr. Akilu Yunusa-Kaltungo, PhD, FHEA, CEng, MNSE, MNIM, and also a fellow of FIMechE. So because our guest speaker is the technical secretary, our vice chairman, engineer Professor Adebisi, will be taking the speaker's bio after the chairman's opening remarks. My name is Engineer Patrick Obidoyin. I'm the publicity secretary of NSE Manchester branch. Permit me to recognize a few individuals today. We're all distinguished, but permit me to recognize a few personalities in our midst. We recognize Engineer Babagana Mohammed, if he's on here with us. He's been invited to join. We also recognize our branch patron and past president of NSE, Engineer Ademola Olorunfemi. We also recognize any National ESCO member present here. We also recognize chairman of our sister branch, NSE London branch, Engineer Theo Odunlami, and NSE Glasgow branch, Engineer Dr. Adediran. We recognize our own chairman, Engineer Dr. Obuks Ejokumo, our vice chair, Engineer Professor Adebisi Bamidele, Engineer Dr. Irene Okadi, our General Secretary. We recognize all our executives present. You are all recognized. We also recognize all our branch members, all members of NSE Manchester branch. We recognize you all. So I will give the floor now to Engineer Dr. Obuks for the chairman's opening remarks. Thank you.
Thank you very much, Patrick Obidoyin, for that warm welcome. Good evening, one and all. It's a delight and pleasure to warmly welcome you to our third general meeting and technical section for the year 2021. By way of opening remark, I want to first and foremostly recognize the continued support of our president, Babagana, who has been very supportive of the branch, and also Alex Momo, the executive secretary, who have been very supportive of our branch and helping us to ensure that our sessions are posted on the national database. So we are very grateful to them. In way of opening remark, I just have three items. One is on membership. I think we have been encouraged from the national level to ensure that members continue to update their accounts to ensure that the accounts are on zero balance at all times. So please, I know we have been doing very well. I encourage members to ensure that they continue to do that. Secondly, at our general meeting today, we'll be deciding on the date of our inauguration as a branch. We are yet to be formally inaugurated by the president, and we are going to fix a date for that inauguration to occur, be it virtually at the end of this meeting. And very lastly, on group dynamics, a lot of activities has happened, and I'm sure our chairman of our committees that we have set up to look into group dynamics will be giving us updates on how well we have done as of today. On that note, I will stop and very warmly invite our able Vice Chairman, Engineer Professor Adebisi, to please come and usher our very own guest speaker, who I share the same floor with. Professor Adebisi, please.
All right, thank you, Mr. Chairman. Thank you, everyone. Good afternoon once again. It's my pleasure to introduce Dr. Akilu Yunusa-Kaltungo. As he's been introduced before, he has PhD, he's a fellow of FIMechE, a fellow of Higher Education Academy, chartered engineer, member of Nigerian Society of Engineers, and so on. He's a senior lecturer in the Department of Mechanical, Aerospace and Civil Engineering at the University of Manchester. Akilu obtained his bachelor's in mechanical engineering from the University of Maiduguri in 2002, a master's in reliability engineering and asset management from the University of Manchester in 2009, a postgraduate diploma in business management from Abubakar Tafawa Balewa University in 2011, and then he obtained his PhD in vibration-based condition monitoring of rotating machines from the University of Manchester in 2015. He has research expertise in safety management, operational reliability, industrial maintenance, rotating machinery, fault diagnosis, multi-sensor and multi-features data fusion, safety management systems, learning from failures through reliability tools, asset management, major overhaul, outages, shutdown, and turnaround. He has recently served as principal investigator for 2 projects funded by the EPSRC and the Lloyd's Register Foundation. His Lloyd's Register Foundation funded projects involve multidisciplinary collaborations between various international academic and industrial organizations to investigate how health indicators can be better incorporated into existing occupational safety performance indicators. His EPSRC funded research project focused on the development of safer drone-based inspection and stock estimation mechanism for confined spaces so as to minimize human exposure to inherent hazards. This is the first ever robot-based practical intervention for stockpile monitoring in cement plants in the world. He is currently a co-investigator on an ongoing project, Keeping UK Buildings Safe, a research grant funded by the Health and Safety Executives UK. He has published over 65 technical articles, with majority of the journal articles in high impact journals. His conference articles have been mostly published in renowned peer-reviewed conferences such as ASME Turbo Expo, IEEE, FIMechE, BM, etc. He has also published a book titled Condition Monitoring, a Simple and Practical Approach. Akilu has delivered keynote lectures at several international conferences and is a member of several engineering committees within and outside the UK, including British Standard Institute, for reviewing several ISO and BSI standards. He is also a chartered engineer with Engineering Council UK, a fellow of the Institution of Mechanical Engineering, a member of FIMechE Safety and Reliability Working Group, and holds a NEBOSH International General Certificate in Occupational Health and Safety. Prior to joining the University of Manchester, UK as an academic, Akilu spent over a decade in various roles within the world's largest cement and building materials manufacturing organization, i.e. Lafarge-Holcim PLC. At Lafarge-Holcim, Akilu served as mechanical execution engineer, reliability method engineer, plant operation model champion, project core team lead, e-learning country administrator for Benin Republic and Nigeria, training and development manager, health and safety manager, and maintenance manager. While serving in the aforementioned roles, he was part of safety audit and plant commissioning teams, including leading several of such teams for cement plants in Egypt, Kenya, Uganda, Zambia, Nigeria, and so on. Akilu is also the current regional secretary, Northwest England, of the Institution of Mechanical Engineers, FIMechE, as well as the Technical Secretary of Nigerian Society of Engineers, Manchester branch. Please join me in welcoming our special guest for today, who happens to be one of our own, Dr. Akilu Yunusa-Kaltungo. The floor is yours.
Thank you very much, Prof. I almost didn't realize that was you were talking about me. Thank you very much. I'm just going to share my screen. Can everyone see my screen?
Yes, we can.
Yes.
And in full screen?
Yes.
Okay. So thank you very much. There isn't much to say about myself. So today we shall be carrying on with the quarter's theme, which is energy management. For those of us that attended the last technical session, would recall that we had an amazing presentation from Dr. Masood with regards to energy management, but this was more focused on the electrical side. He also did mention that the majority, more than 60% of failures in energy systems are due to mechanical components. So today's talk is going to be more of a complementary presentation, although in a different kind of light to what we had last month. So humans by nature are obsessed with data, which is not necessarily a bad thing. However, our core rationale behind collecting any set of data should be the ability of such data to create value. We do know that data collection is expensive, data processing is expensive, and most importantly, when we have too much data and we become buried in data, we're unable to take decisions because the time available to make such decisions through diagnosis of such data becomes unrealistic. Okay, so tonight we shall be looking at some of the ways by which we can better optimize our data, or at least think about what the implication of data quantities that we acquire have. Okay, so our content for this evening would be, we'll look through some fundamental definitions. I'm very conscious of the fact that this is a very, the audience here is very diverse. So I'd like to pick on some very simple terms that would be coming across throughout the presentation, and I'd like to define them. Hopefully at the end of today, the outcome of this presentation will all be experts in the diagnosis of failures in mechanical systems without really doing too much of the complex math. So, so we'll be looking at why engineering systems fail, generic reasons, evolution of failure management, integration of maintenance strategies, typical energy systems. We'll be looking at steam turbines because steam turbines account for roughly 80% or are involved in some shape or form of up to 80% of energy generation. Then we'll look at one of the fundamental standards behind data collection in the condition monitoring sense, which is ISO 10816, and how the impact such standards have on our perception of data quantity. We'll look at typical data collection regime on energy systems and their shortfalls, potential remedies for those, and we'll look at hierarchy. We'll wrap up with hierarchy of data value. Now, data can be defined as, I define data as carefully gathered and reliable units of information that support decision-making and value creation. So now two things here to look at: decision-making and value creation. So what this should tell us, or the thoughts that should be triggered by these two terms, is if it's not going to support decision-making or value creation, then we shouldn't be collecting such data. Of course, as humans, sometimes we collect data and we keep for future expectation of use. I've fallen into that several times. I believe I collected 5 times more data than I required at my PhD level, which I'm still distributing to some of my PhD students currently. So secondly, we'll be looking at what is failure. Now, failure is defined as the total or partial inability of an asset or component to perform the functions for which it was acquired under specific conditions and over a specific time period. Now, take note, I've highlighted partial and total. Now, depending on the school of thought, the Japanese will define failure as partial inability. In the West, it was defined as total, so only when something breaks down. Now, depending on the definition you go with, this would significantly affect your maintenance strategy. Now, let's take, for example, a pump. If a pump was acquired to deliver 1,000 liters of water per hour, if that pump is delivering 900 liters per hour, which is approximately 90%, that pump has not failed if you're using the total definition. However, if you're using the partial, that is failure, because those 10% you're losing could be impacting on your production, or could be making that pump become a bottleneck along your process line. Okay, we'll also look at things like MTBF, which is mean time between failures, and MTTF, mean time to failures. Now, these two are sometimes used interchangeably. However, MTBF is most suitable for repairable systems. So systems like gearboxes, for instance, if a gearbox fails, or if your brake system fails, you replace things like brake pads or things. So these are repairable systems. And then you start counting the number of hours they run. So the way you would calculate MTBF, for example, is you fix it, you start the component, it runs for N number of hours, it breaks down, you repair it, and then you start counting again, and the cycle continues. For MTTF, on the contrary, you're thinking of just the first failure. So these are non-repairable systems. An example of this would be the light bulbs in our houses. So we don't monitor the current going through the light bulbs in our houses. So once they fail, we just replace them. So these are non-repairable systems. Ammunitions are non-repairable systems, but the arms are repairable systems, okay? MTTR is the mean time to repair. So this is how long it takes you to restore a failed component to a state of working condition under specified conditions and over a specified period of time. Now, natural frequency is the frequency at which a body or system tends to oscillate or vibrate in the presence of a driving force. If it's a drive chain, then maybe the electric motor is the driving force, or the excitation force. Now, this is a very, very interesting term, especially for energy systems. So ideally, the natural frequency could be referred to as the DNA of a machine. And it is very crucial, especially during commissioning, to know the natural frequency of assets you're installing, especially power systems like turbines and so on and so forth. Because without knowing the natural frequency, you would not know what speeds to avoid. Now, this is something I've been part of a lot of commissioning teams. This is not very common in practice, okay? Now, there's always the assumption that the manufacturer said, if you do this and this, the natural frequency should be around this. The same machine manufactured by the same manufacturer in the same batch, dispatched at the same time, could act very differently on the field. If you mount one of such machines on springs and another on concrete or steel bed, they would have different natural frequencies because the stiffness to mass ratio would differ. So it's very important for you to know the natural frequency. So it's like knowing the DNA of the machine. And then you know if the natural frequency is 100 hertz. What that tells you is do not run around 100 hertz, or you would be causing resonance, and resonance leads to fatigue failure. So this is always the problem, and this is why we kill our equipment sometimes right from when we install them. Okay, so now let's look at, this is a 20-year data spread of typical failures within steam turbine components. Now, if we remember from February, Masood said around 60 to 65% of failures are mechanical in nature, which means if you can tackle the mechanical failures of mechanical components, you can actually tackle between 60 to 80% of your failures, which would be incredible. Now, so doing a Pareto plot, you find out that the dominant failures from here are things like the low pressure turbine buckets or blades, and so on and so forth. If you sum up the failures caused by these components, they're approximately 80%. Now, Pareto was an Italian professor who studied wealth distribution in Italy, I think in the late 1800s to early 1900s, and found that 80% of Italian wealth is being controlled by 20% of the population. I'm sure a lot of us can relate to such concepts. And this goes through all walks of life. In the field, I've done several Pareto analyses with spare parts. You'd find out 80% of your spare part cost is caused by around 20% of the spares, okay? So these are what we refer to as critical spares. So what it means is, if we can tackle these components, just these components, then we have a chance of addressing 80% of our problems. So what it means, being strategic, you would want to focus most of your efforts on this few, okay, rather than on the rest, because you have more to gain, okay, in terms of benefits and efforts analysis. Now, traditionally, repair and replace is mainly a function of maintenance, and this is how we've addressed failures over the years. However, why do our components fail in the first place? These are generic reasons anyway. There could be so many of them, but most of the causes of failure can be attributed to one or some of these. So the two main reasons are inherent weakness or victimization. So inherent in the sense that either it's been faulty from design or during installation, or victimized during operation. So like you've been used for different purposes. So let's look at some of the causes of inherent weakness. So cheap option, poor design, substandard material, or inaccurate manufacturing processes. Now, in regards to victimization, it could be either either functionally or physically. So with functionally, it could be poor installation. One reason for that could be not knowing the natural frequency and then operating the equipment at the wrong speed. It could be poor commissioning. Sometimes you're meant to commission over 3 months with with incremental loads, but because we do feel that would take too much time and we want to quickly cut down the cost of the commissioning team and quickly hand over the equipment, we shorten that and accelerate the load. So there's a difference between incremental loads and accelerated life testing. You would usually do accelerated life testing as part of your design tests in the factory. During commissioning, rather, you want to steadily load your equipment to see how it will behave, because you would want such large equipment to last for up to 20-25 years, okay? So maloperation, change of intent. Sometimes we use one component for a different purpose. I've seen this happen in the field several times. You run out of these spares. For example, you're replacing a floating bearing with a fixed bearing when you know that one should have a collar and the other shouldn't. But because you've run out of this spare, you just say, okay, they have the same internal diameter and they will fit on the same shaft, so let's just use it, without knowing that you're compromising the lifespan of the entire drivetrain. Then modification. Some of us make modifications to equipment without any change management processes. Now, physically, we have deterioration and damage. Now, we could be damaged during transportation. Some of these very expensive components, like the steam turbine, for example, the blades are made from specialized steel. So usually before fixing them, putting them into service, you will need to coat them with bearing and maybe some towels or rags, to prevent corrosion and deterioration in stores, on transit, and on site. So all these things are being overlooked, but they contribute immensely to failures, even before you start running the equipment. Also, some of our spare parts deteriorate even in the supplier store or in our own store before we even put them into practice. So these are some of the main reasons why our assets behave differently from the way we initially wanted them to. Now, people always ask, so where is human nature here? If you look very well, you'd see that human factor can fit into, you can have human factor associated with each and every one of these terms, okay? Now, how do we prevent this? The traditional answer will be through maintenance or condition monitoring or asset management. However, maintenance has evolved over time, okay? In the past, it used to be called first generation. And during the first generation, because competition was minimal, there wasn't much of globalization. customers were willing to wait for the producer of their component, no matter how long it takes. You know, so market was more monopolistic rather than perfect competition that we have these days. So in those days, you just keep a store of with so many spare parts, a large workforce, and there is no need for planning, because once the equipment breaks down, you just put in another one and just get 10, 15 technicians to go replace it. And the customer is there waiting. There's no problem. I mean, when I first joined Lafarge, I think the turnover time or the delivery time from order of cement to delivery to the client sometimes takes up to 6, 7 months. These days, who would wait that long when there are so many cement manufacturers neck and neck to each other? So because of the environment then, it was very easy to operate under that. However, what did happen is this was very expensive practice and it was unsustainable. Okay, so people began to think of, okay, moving away from this. And then we moved to the second generation where people began to do some timed repairs. So we were like, okay, we know that carbon brushes wear after 6 months. So we can order for our carbon brushes around month 5. Why are we ordering in month 5? We've saved ourselves 5 months of keeping stock in the stores, and we've reduced our working capital as well. So we can use that money for something else rather than tying it down on spares in our stores for 5 months, which is not really generating any revenue or income. So that's one. Secondly, we do not need to keep large stores, so we don't need to pay so much for warehousing. Okay, so we can keep very small because our stock turnover is very high. People began to, and in order to achieve that, you had to plan jobs, you had to allocate people to jobs, you had to let people know that in 6 months you'll be replacing carbon brushes. So the tools and equipment you need for that job should be ready in 6 months. However, there will still be lots of spares, because the implication of timed repairs is that you're replacing assets based on time. Now you might be replacing an asset that is still fit for purpose. Okay, and naturally, when you take out any component you replace and put in a new one, you're further shifting your what we call the bathtub towards the infant mortality stage. So you're increasing the possibility of failure at early stage as well. But availability increased and the costs, operational costs, were lower than in the first generation, and asset longevity increased as well. Okay, now in order to further improve that, we moved to third generation, which is what everyone calls condition monitoring or condition-based maintenance, which is the buzzword. It's been the buzzword for the last 20, 30, 40 years. Now people began to do risk studies, people began to do failure modes and effect criticality analysis. People began to do fault tree analysis, event tree analysis, reliability, availability, and maintainability studies. Intelligent systems came in. You started having smart sensors, smart diagnostic systems. There was a lot of cross-skilling. So there wasn't one technician does only the fitting of bearings, or one technician only machines gears. So you had a cross-functional team. You had a technician that could fix gears. You had the same technician that could also operate the crane. So you had cross-functionality, and by doing that, you're able to rationalize your workforce. And then what would happen? High availability, high reliability, high safety, high product quality, and asset longevity. However, the further you move, yeah, thank you. Now, the higher you move up this hierarchy, the more your data requirements. Okay, now condition monitoring is very, very data intensive, and of course we know data doesn't come cheap. Now, besides being data intensive, there's always this notion that condition monitoring is the best strategy for every maintenance problem. This, if you're not going to take anything away from today's lesson, you should take this away at least. Now, all maintenance strategies, breakdown maintenance, planned preventive maintenance, and condition-based maintenance, are all useful in their own rights. Now, if I give you an example, a typical industrial site would have lighting systems, will have turbines, we have all that. I don't think it would be cost effective for anyone to perform condition monitoring on light bulbs, because the effort does not justify the impact of failure. You don't want to be monitoring the amount of current going through your light bulbs. It's cheaper for you to wait for them to fail and you replace them. In essence, you're implementing run to failure strategy, okay, which is first generation. Again, there are some assets that you know their failure patterns. So for example, you know for sure that your carbon brushes on your electric motors, your induction motors will wear out after 6 months. So then that you can implement planned preventive maintenance because they have a definite wear out pattern. And then for those assets that are characterized by random failures that you cannot predict their failure patterns unless through specialized tools and sensors, you dedicate those to condition monitoring. And they're usually a small percentage of your wide population, because if you use condition monitoring for everything, you'll be like killing, in some instances, you'll be killing an ant with an axe. Okay, so it's not cost effective. And yes, you might be detecting failure, but at a very, very ridiculous cost. So here I'm just giving a hypothetical example with a case study. The percentage distribution would be different for individual plants anyway. So let's say first everything starts with a business review where you define how you want to run, how much you want to produce, and what you would want your year to look like as an organization. In order to do that, you would need to make reference to some benchmarks or best practices, which could be from sister plants, from competitors, or from trade associations, okay? Now, with that, you would conduct what we refer to as functional analysis to clearly define because at the business level, you're setting the tone. So for example, the business level analysis would cover the entire organization, including your HR, your safety, your operations, and so on and so forth. But then within that, here, you're focusing on your operational requirements now. So maintenance and production, for example. And in order to achieve that, you will need to make reference to some statutory requirements, because these are must-dos, they're not optional. So if you have pressure vessels, there's a requirement for you to pressure test them maybe every once in 2 years, and you need to submit those certificates, or you'll be breaking the law with the factory inspectors and safety inspectors. So once you've done your functional analysis, you now do what we refer to as criticality review, where you would define your criticality matrix, and with that, you will allocate risk priority numbers based on things like severity of failure, frequency of failure, impact of failure in terms of downtime, and so on and so forth. And then you would rank them. You would find out that for this case now, 10% of these are highly critical. And you can apply things like RCM, reliability centered maintenance, and so on and so forth. Now, the medium criticality ones, you can base this on existing experience within your plant. So there's a way we've been doing this, and we're very confident because the impact of failure of this component is medium. So it's not the craziest thing, okay? And then for those with extremely low impacts, you would apply what we call things like structure review of tasks using your monthly proactive. So you just replicate your monthly PMs or preventive maintenance activities, because these are low impact failures. And once you've done that, you load all of this into your maintenance task and form what we call your maintenance workload. Once you have that, then it becomes easy for you to define the kind of spares you need. You're also able to develop an organization that will implement these based on skills and experience. You load this into either your maintenance management system or your computerized maintenance management system. And at the end of the day, you execute your task. Now, you would find that typically, now for this case study, 55% of activities are condition-based, 20% are planned preventive, 10% are design out. Now, for design out are those activities that have high frequency of failures and high impact of failure. So high. So when they fail, they have significant impact. Now, that impact could be in the sense that it might take a very long time for them to be repaired, so your downtime cost is huge. Or there might be things like if it's pressure vessels in a petrochemical industry, it could lead to loss of containment, which could have a lot of environmental impacts or hazards, which could lead to litigations and a lot of cost and loss of reputation. So this kind of that have high impact and high frequency, it's better to design out or design the risk out, okay? And then about 10% are the least critical ones. You run them to failure, wait them for them to fail, and then replace them. There is no need sweating on these ones. And you have your statutory activities with the remaining 5%. And of course, you need to feed all of this back, and the process continues on and on. So here, what I'm trying to point out here is that every single maintenance strategy has its place, and you need to combine all of them together to have a holistic maintenance strategy for you to be cost effective. Okay. Now, this is just a typical steam turbine, and like I said at the beginning, it's been stated that steam turbines are in some shape or form are involved with up to 80% of energy generation across the globe. Now, this is just a schematic representation of such. Now, the steam drives the turbines. So let's say you have your high pressure, intermediate pressure, and your low pressure. The steam drives the turbines, and your steam could be your steam. When we say steam turbine, a lot of people think of just fossil fuel based or coal based and things like that. Your steam can be generated using renewable sources. Okay, so there's nothing special about that. And so you convert heat energy to mechanical and to electrical. So you draw out, you generate either your electric current, which you take out with your slip rings and carbon brushes, or maybe if it's DC, you're pulling out, maybe you have some commutator, you have some commutators there. So now, having said that, on each of these turbines, for example, each of these turbines will be resting on bearings. They'll be resting on bearings, and there will be so many of them. I mean, depending on the size or the electric or the amount of energy being generated, you could have 30, 40, 50, depending on the size. Okay. Now, ISO states that you should collect data from 3 individual locations. So ISO 10816. Vertical, you measure from vertical, radial, and axial. Okay. So you collect data and you analyze them. So think about having 50 bearings on a machine. So each time your inspector goes to measure, monitor vibration, for example, they'll be measuring at what? 90 positions, collecting data from 90 positions. Now, if he has 10, 20 machines spread across the site, he's going to do that times n number of machines. And then he would come back, analyze all of those data, and then take a decision upon which whoever the manager is will decide on which spare parts or when to take out this machine for maintenance. Now, this is very unrealistic. And this is why we collect so much data on site, but we're still experiencing so much failures. So something is definitely not happening in the right direction. So let's look at the typical, let's strip it down and say this is a schematic representation of the mechanical side of a typical turbine. You'd be taking, let's say, so it's rotating. So you're collecting spectrum in vertical direction and in horizontal direction from each bearing. So you have 4 spectra in the horizontal direction. You're doing the same in the vertical direction, okay? Now, you're also, because now the shaft is rotating within a bearing, you want to continuously measure the concentricity of the shaft within the bearing housing. So you're collecting what we call the orbit, you're measuring the orbit plot, another set of data. Okay, you want to know, because of course there is heat from steam interacting with rotating equipment. So you're generating high temperatures. You want to make sure that the temperature between the shaft and the bearing is acceptable, and the oil that is lubricating the shaft and bearing. Now, so you want to use maybe infrared thermography to measure temperature across individual bearings, another set of data. You now also, turbines are heavily dependent on blades. And if you have one, each of these blades sometimes could cost between 5,000 to 10,000 pounds per one. A typical turbine, maybe 500 megawatt turbine, could have up to maybe 30 stages, and each stage could have 120 blades. So calculate how many blades multiplied by maybe 5,000 pounds. So you don't want to lose any of these blades. Now, if these blades, what you do is you install sensors across each stage, so that if there is a crack on the blade, the natural frequency would change. Remember natural frequency from the beginning, because when there's the crack, the blade loses stiffness, and then the time, what they call tip timing, the time it takes it to complete one cycle would change because of that loss of stiffness. So it will start fluttering. So you measure that as well. And then for you to ensure that all of this is happening at the right, you're getting the right pulses, you have a tacho sensor. A tacho sensor works on the same principle as the speed sensor in the dashboard of our cars. Now, because you're coupling the turbine to an electric motor through coupling, there is no guarantee that the speed of the rotor shaft is exactly the same as that of the turbine shaft, which is why you use this because of what's called slip, okay? So you look at all of this just on one turbine, and you need to analyze all of this data to make decision. You would have to be a Superman to actually do something tangible. So here I've created about a few scenarios. So let's assume that you have a single steam turbine with several faults, which is operating at various speeds, okay? Because there would always be variable speed motors, okay? Or variable speed equipment. They run at different speeds depending on how much energy you want to generate. If this data were to be collected from a critical industrial turbine that has 30 bearings by condition monitoring inspector using handheld devices, so they'll be collecting this amount of data. Now we're not even looking at the sampling rate. Sometimes you collect this data at up to 10,000 or 20,000 samples per second, okay? Now, you would have thermograms, you have a tacho plot, you have all of this. You would also do wear debris and oil analysis, all of this. So to collect this data, a super inspector might take approximately, let's say 5 minutes to treat each of the bearings. That will be what, 450 minutes, okay? And then another 150 minutes for thermography. How many minutes are there in a day? Can this be done remotely? Absolutely, yes. However, you will need to install permanent sensors on each of the measurement locations, which would be costly. And of course, that does not solve the data intensity problem, okay? Now, so let's look at how this would work. So let's say that's your shaft, a cross section of the shaft. And then you have the bearing and its housing. And then you have the sensor, the accelerometer for measurement. And this is operating at, say, 3 speeds, slow, medium, and fast, okay? So when it's operating slow, you generate data, and then maybe with all those features, you analyze. You're supposed to have an algorithm that will take a decision. Medium, you do the same. Medium speed, you do the same. Fast, you do the same. And then you're supposed to you store this in your history or your historical database, take a decision, and hopefully avert failure, which is not always the case, okay? Unless if your process is very, very capital intensive or labor intensive. Now, second scenario, let's say on your site, you have several turbines. Some are installed in marshy areas where you need concrete bed. Some are installed on maybe rooftops. You use springs to dampen the vibration. Some are installed on steel beds. Now, they're exactly the same turbines with exactly the same components configuration, but they will have different natural frequencies. So they would have different DNAs and they would act in different ways, okay? So let's say you have steel, springs, and concrete. Now, you would need to treat each of these turbines separately because you need to analyze the data in different ways, okay? Now, data size is equals to scenario 1 times number of turbines at the very least. So when do you actually have the time to analyze this data set and take a decision? I used to be in charge of inspectors, condition monitoring inspectors at one of the plants I worked before joining the university. And what happens is sometimes because they spend so much time collecting data on the field, sometimes they go out on their routes around 8 or 9 in the morning. They come back to the office after collecting all of the data around 2, 3, and they're expected to log in all of those data, analyze them, and pass out the results because the manager will need to discuss that result at the production meeting the next day. Well, what do they have to do? They can't tell the manager they've not analyzed the data. So what? You just tell your manager everything is fine until a failure happens. That is the problem. Okay, so what happens is data intensiveness will always lead to complexity and higher diagnosis time, which will always be costly. Okay, it will always cost us money. Now, how can we optimize data manage? How can we optimize data in the sense of condition monitoring? Now, let's. I would like to draw our attention to the fact that these are centered around things, ongoing work, or things that I have done or still doing. There will be several other initiatives that are happening. There will be several incredible activities that are happening. But then one approach that has proven very, very useful is through data fusion. So with data fusion, you can harmonize all of the data you collect irrespective of the number of locations. Either you can fuse those data either at sensor level. So when you're collecting from the sensors themselves, you can fuse the data and then move to the feature, extract your features, and then take a decision. Or you can allow different sensors to give you data and then process that data, extract the features, and fuse the features themselves. So an example is you could be looking at the harmonic components of a vibration spectrum, and then you just pick up the amplitudes, or you look at the crest factor, or you do kurtosis or root mean square velocity, or different, any kind of feature, or temperature. And then these are features. You can harmonize them and then take decision. And sometimes you can analyze temperature separately, analyze vibration separately, make a decision on vibration, make a decision on temperature, make a decision on oil analysis, and then combine the decisions, which is what happens at the decision level. So let me just give you an overview of what we've done practically, which has shown a lot of potential over the years. So this is just a laboratory scale of a turbine. So there will be your source of excitation, and let's say each of these disks represents one stage of the turbine. So naturally, those holes there will be where you would mount. You can mount your blades. Okay, so let's say that is your high pressure, intermediate pressure, low pressure. Okay, and that's those are your couplings, and so that is it, and just a scaled down representation of what you would have on site. Now, take note here, ISO says collect data at 3 locations, but here we're trying to collect data at 1 location. So you're rationalizing data from the sensor level by 66%. So you're only using 33% of what should have been. And we're collecting at 45 degrees. The thinking here is this: if you do your resolution of forces, so vertical and horizontal, if you resolve those forces, you might be able to get similar response at the diagonal, which is the thinking here, okay? And then, so what did we do? We had 720 scenarios were considered on 2 scaled down models of steam turbines, okay? Now, so each of those ran at 3 speeds. There were 6 cases. 6 of the most commonly encountered failures in the industry were considered. So 1 was the healthy, a baseline case, a bent shaft, okay, because of the heat that happens, the high temperatures at which you run these turbines. There's always buckling of the shaft. If your coast down or ramp up process is not adequately done, you could bend. It's very common for people to bend the turbine shaft, okay? And then there's a shaft crack, which is also very common. Looseness. Sometimes it could be looseness of bearing support or looseness of blades and things like that. Then misalignment, because you're coupling your generator to the turbine, there's always that possibility of misalignment. And then rub. So if you've not properly aligned the turbine, it could be rubbing against the cases. So these are the cases we've considered, and we're collecting 20 data sets per case, okay, on each of these experimental rigs. Now, these rigs are exactly the same machines, but the flexibilities of their supports were different. So we simulated that one was mounted on springs on site and the other was mounted on concrete. So their DNAs were different. Now, so this is what you have, and we've scaled down the sensors. You collect data through your data signal processing system to your data acquisition and so on and so forth. Now, you would have 1 spectrum per bearing. Now, according to ISO, you would have had 3 spectra per bearing. Now we are having one spectrum per bearing. So there are 4 bearings here, so 4 spectra. And we're now fusing the Fourier transforms of each of those spectra. So instead of even analyzing 4 spectra, you're fusing together to have one spectrum. So you don't need a vibration expert. So you can have just a normal operator look at only one spectrum. And this would be, he can just look at it, okay, what is the vibration level? It is acceptable. He will only call the maintenance expert when the vibration level is out of the normal range. So you're saving manpower, you're saving hours, and you're allowing the vibration experts to focus on very critical industrial activities rather than calling them to just come and analyze spectra every now and then. Okay, so and another beauty of this data fusion approach is that we're also using something called the coherence. Now, because of the heat, the movement of steam and the speed splashing against the blade, there's a lot of noise. So that background noise can mask the actual behavior of the failure characteristics. So you might be looking at noise pattern and thinking that you're diagnosing faults. So with these, coherence, it suppresses the noise level. So it only gives you the correlation between the actual signals from the sensors, okay? So by that, you've reduced your data by 66%, which is lovely. By 2/3. Now, the spectrum calculation you saw, the spectrum you saw earlier are generated using this very simple mathematical equation. And this spectra have been used in several fields. In the medicals, you'd have things like the ECG, where you have all those sensors across different parts of the human body. They plot the spectra. And because the human body also has its own natural frequency, for example, an average sized man standing would have a natural frequency of around 7 hertz. The same man squatting would have a natural frequency of around 8.5, because of course, when you squat, then you've increased stiffness and you can't easily fall. So the natural frequency would increase. So, however, what we found is by the conventional way of calculating those amplitude spectra, which you saw previously here, is that you're multiplying the Fourier transform by its complex conjugates. Now, what happens is when you do that, it's like multiplying one person by his own mirror image. You will lose the complex element. So if we say, and we know, so let's say, for example, what would naturally happen is, say we have something like A plus JB. These are complex numbers. And its complex conjugate, which is its mirror image, will be A minus JB. So the mathematicians in the house can correct me when I get it wrong. It's been a while. Now, when you multiply this out, you would get A squared plus B squared. Now, this is a real number. You've lost the J. The J is the complex component. The implication of this is now this becomes a scalar quantity, and so it has no direction. What it means is you cannot estimate the severity or the direction of the fault because you've lost your phase angle. Now here, you have that, but now you've lost it. So you're only dependent on the magnitude, which can be similar for different faults. For example, misalignment and crack can have similar magnitude distributions, okay? Which was why we've moved on to this approach where we use the third order spectra. And the third order spectra is just you're multiplying this arrangement by another Fourier transform. So you're bringing back the phase, okay? And then fourth order like that as well, adding more phase information so that you can have better diagnosis and better characterization and differentiation of different faults. So for this plot, for example, the size of the sphere is a representation of the amplitude. The bigger it is, the bigger the higher the amplitude. And you can see these are different faults. For example, this is crack, this is misalignment, this is unbalance, and so on and so forth, okay? And so what do you get in the end? You get like a distribution plot whereby this is the cluster of healthy. So a healthy machine at the start, would all the data you collect will continue to remain in this cluster, okay? Once it begins to move to a different cluster, then you know there is a fault. Now you would have generated your historical database and created the characteristic for different faults. So here is a fault like maybe this is crack, this is misalignment, this is rub, these are this. So you would have those patterns. And when you introduce new data, if new data sets come here, you know that your machine is moving towards that fault. If it moves here, you know it's moving towards that fault. So for example, maybe some of these faults will require expert support from outside the country where your machine is domiciled. So if it's a crack, you will know that, okay, I need to bring in the guy from Germany, and you can start preparing for the guy in Germany, okay? If you don't have something like this, you just know there is a fault in the machine, there's high vibration. Are you going to bring in all the experts from all over the world? That is the problem. So, so this is why it's very important to rationalize data, and then you can build a history of each of these fault patterns. Of course, there is the possibility that you have a fault that does not fall into any of these clusters. So you will use that kind of data to develop a new fault class. Now here you would see PC2, PC1. This we stumbled into this solution, I'll tell you, which is how it happens in research in a lot of times. This is principal component, and the initial plan was to use principal component to reduce data dimensionality, okay, and remove redundancy, data redundancy. But what we found out that when we applied PCA, which is a very simple technique, it's a linear classifier, we found out that it was able to distinguish the faults clearly. So what we were going to use as an intermediate step became a solution itself, which was very, very encouraging. Okay, so this is what happens. So if data moves from crack to misalignment, it can be in healthy, and all those can be analyzed and tracked in real time without the intervention of an expert. You will only need to bring in an expert when it moves away from the healthy region. So what are the next steps? The next steps now are to automate the process, introduce some machine learning. I have 2 of my PhD students working on this as we speak, and the results are becoming more and more refined and very, 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 very encouraging. So, however, before we wrap up, we know that when we do all of these things, we need to report our findings, okay? However, do we consider what we report and the implication of what we report? Do we look at the conflict of reporting? So first is when we complete our task, maybe it's a maintenance task or an installation task or an operational task, we want to report what we planned versus what actually happened, okay? And we'll generate data from that again. But then, why do we report? Are we reporting merely to comply with the procedure, or are we really reporting to improve performance? Will the data be used in the future? And can we define what the improvements would achieve by reporting that particular data? If we think about all these things, this would change our mindset towards the type and quantity of data we collect, okay? Now, who does the reporting? Will it be the work crews, their supervisors, or their team leaders? Okay. Do we have the number of staff to handle this? Are they competent enough? So do they have the aptitude? Okay. Are they willing? So attitude now. Do they have any hidden agendas? So are they demotivated? Would they give you the right data? Would they take the right decision? How would you report? Electronically, written, or verbally? Remember, computer data is out of sight. So once you log it onto the computer, you're not seeing what you've put in. Handwritten data requires manual collation and takes time. Where are you going to make your reports? Through face-to-face meetings or via computer terminals? Meetings take time and requires a lot of vital people, which is again your increasing demand hours, okay? You can't question what has been put in the computer. What would you be reporting? Would you be generating a formal data report, or would you be reporting by exception? Reporting by exception is you just reporting what you think is accurate. Now, what is accurate depends on who is defining accuracy as well. Or would you let people just report based on their discretion? Remember, too much data could overload the system, and too little would be useless because you cannot take decisions based on them. When would you submit the report? Would it be as soon as possible? Would it be daily? Would it be weekly, monthly, yearly? Reporting takes time. So if you want to do it daily or as soon as possible, you should remember the reporting takes time. And if you leave it for too long, people will now need to start thinking from, will now need to start generating such from their memory. And we all know that that will lead us nowhere because of the reliability of the brain. Okay. So to wrap up today's session, we'll be looking at hierarchy of data value, just to remind you all of what we've spoken about. Now, the various data that we acquire during our operations offer the greatest value when they support our decision-making process. This was what we started with. Remember the definition of data at the beginning of the presentation. So if we just collect raw data, for example, number of turbine failures that have happened in this year. Yes, that's data and it has some value, but then what? Number of failures, then what? What can you do else besides knowing number of failures? However, if you tell me that the turbines ran for this number of hours before they failed and ran for this number of hours after repair, and it took n number of hours to repair them, then I know, okay, it took n number of hours to repair them, so it will cost n number of maintenance work hours. Okay, we know that MTTF is this, so after so we need to replace this particular component. So you've increased the value because you've given better, higher quality of information. Now, if you now go further and use that knowledge to benchmark yourself against other plants. So we have 170 hours of MTBF, but our competitors have 320 hours. Why? What are they doing that we are not doing? Now you're beginning to investigate, and for each of these investigations, you're increasing the data value. And then once you now decide on using that information to avert the failure, you get the maximum value from the data you collect, which does not have to be the bulkiest data anyway. Okay, so with that, I have come to the end of my presentation. Here are some of the references for some of the information contained. And again, some of the figures I've taken from online. And with that, I would like to say thank you for the opportunity. And I'm happy to take any questions you may have. Thank you.
Thank you very much, Akilu, for that wonderful and insightful presentation. I got some push to stop you in between, but I was afraid to stop because I knew you were speaking on a topic that you love so much. But what that means is that we may have eaten into question time. However, I think it will still be out of place not to ask some questions. Please, Patrick, can you guide me? If maybe I've missed it, I've not seen any question on the chat box. If there is any, I will want to read it out, but I haven't seen any. So if there's no question, do I want to invite?
Sorry, I think I have a question.
Yes, sir.
Camille?
Yeah.
Please type your question. I will.
Dr. Bond.
Yes.
Dr. Books, we also have engineer Dr. Aderi's hand up, please.
Good. I'll pick engineer. He's a mechanical engineer, so I think his question, and he's trained in UMIS, so I think so his question will be very apt. Engineer Dr. Aderi, please.
Yeah, thank you very much, Books. And I want to congratulate the speaker. My PhD thesis actually has to do with reliability assessment of repairable mechanical systems. So as the guy was speaking, he was actually reminding me of many things we studied, mean time between failure, and it's a very, very direct application to industry use. So I want to congratulate you on this, and I think it's very good. And we should think of ways of digging deeper on this.
Thank you, sir.
Well done.
Thank you, sir. Thank you.
Thank you very much, sir. I know we have some dignities to recognize, but is there any other question? While they are typing, maybe let me ask Akilu a question of mine. Akilu, no offense, I know we are very close friends, so this question just came to mind. It's quite interesting that most of the things you've talked about, I can see transaction cost in it, and as professionals, we're always being asked to make decisions. So in other words, our decisions can only be as good as what data we have. Somewhere, I can't remember the slide number. There's a slide where you showed, you referenced the output. In management, we tend to move slightly from output to outcome. So I'll give you an example. You can produce 100 cups of coffee a day. That can be the output, but the outcome is the taste or reaction of people when they take the coffee. You know,
yeah, absolutely.
So I wonder if you can comment on the difference between output and outcome as regards some of the studies you've done.
So yeah, thank you very much. In the sense of condition monitoring, there isn't a lot of separation between the output and the outcome, to be honest, because the output you're getting from the data you're using to make decisions, which will lead to the outcome. Okay, so there isn't much of a difference, because the outcome you want at the end of the day is to avert failure or to reduce your mean time to repair, which is the fundamental thing. So you want to optimize. You have two levers basically. So you either increase your mean time between failures, which is the outcome you want ultimately. Increase your mean time between failures or reduce your mean time to repair. Some people say sometimes push for both, but I am not a fan of that, because sometimes I believe in you optimizing in your areas of strength. So the outcome here would be optimization of your runtime in operation generally.
Thank you very much, Dr. Akilu. I won't see any question, but maybe I use the opportunity to invite one of our senior colleagues here.
Dr. Books.
Yes, please.
There's a question now from one Lanre Aluko, but we also have our patrons hand up for a while now.
Okay, I will come to those two, please. I will invite engineer Margaret Oguntala, who is an engineer, to ask a question, and at the same time use the opportunity to welcome her. She is a member of council and a former vice president of the society, so it's a pleasure to have her in our midst. So, madam, please, you may unmute yourself and give a remark or a question, please. Maybe she is no longer on the call. I move on straight to the question. Who had the question before? The president.
I have seen the question. I think it's Lanre. So the question is, if you after fusing, how do you detect the location of the problem? So there are several approaches here. So the first step is to fuse the data. And why are you fusing the data? You're fusing the data because you want to minimize expert dependence or human subjectivity. So when you fuse the data, you have a pictorial representation or visual map, which can be interpreted by operators who are not experts in vibration. All they need to look at is the data in the right cluster, bottom left-hand corner, which is the healthy cluster. They will only call on the expert when he moves away from there. Then the expert will now need to look at each of the 4 fused data together. That's one approach. The second approach is, remember, you have your phase, and your phase tells you the direction. So from that direction also, each fault is attributable to a particular direction. So I'll give you a very simple example. With a misalignment, you would have a kind of 8 shape in what we call the orbit, okay? And you know that is due to preload, okay? So these are some of the ways, but the main essence here is to minimize data intensiveness. And you would only go to individual spectra once you find data moving away from dedicated clusters.
Thank you very much. I think I will invite our past president and patron, engineer Olorunfemi, to give us a closing comment or ask his question, please. Sir. I know Nigeria, we are running 5G now, so it can't be network. Past president, it can't be network. Okay. Past president, can't hear him. Okay, I have randomly picked one last person to maybe help us that. there's no name, but I can see Rising attached to the sign-up name. Can I invite Rising, please? I'm not sure who that is, but I think Rising, can you please have a question for us?
Thank you so much, Obux. You're being cheeky. You know exactly who this is. This is Akilu's older sister. I'm a plastic surgeon. I don't know anything about engineering, but at least I know Pareto chatting. So thank you very much for a wonderful presentation.
Thank you.
Thank you much, Doctor, for joining us and gracing our occasion. I think that brings us to the end, and perhaps I will invite who is giving the vote of thanks? Patrick, who is it again?
The Financial Secretary, Engineer Ladi.
Ladi, please, you have the floor.
I have the question.
Past President is here.
Chairman, my hand is ready.
You've been called upon, sir.
Thank you, Pato. Don't mind that young chairman. Well, Mr. Chairman, Vice Chairman, very distinguished guest speaker, my boss on the platform, my colleagues. Let me especially recognize Engineer Mrs. Margaret Obitala as well, and other dignitaries. I am not surprised. I've been privileged to visit Akilu's laboratory 2019. So I wasn't surprised when I was turning it out. Every scholar, every speaker, that was fantastic. Congratulations, I enjoyed it all. Manchester, please keep it up. I want to thank everybody for attending. Thank you very much.
Thank you, sir.
Thank you, Past President. I'm happy your 5G is on.
Hello, hello.
Patrick, who is that, please?
Hello.
John Upai.
Okay, please, John, because we want to quickly close this session and move to general meeting. Please, John, after John speaks, Ladi, please just jump in with your vote of thanks, then we can move to general meeting, please.
Yeah, thank you very much, Dr. Kaltungo.
Yes, sir. Thank you, sir. Even though I can't hear clearly, but thank you, sir.
Can you hear me clearly?
Sorry, I didn't hear the middle of the. I think you were breaking in the middle. I think it's frozen.
Can you hear me very well? Hello, can you hear me?
Okay, yeah, now you're back on. You were breaking in between.
Can you hear me?
Yes, now we can.
Hello.
Yes, now we can.
It's better.
Yes, it is. It is.
I'm trying to hear you. I'm trying to.
Yeah, it seems the bandwidth at yours is yeah, because it's showing red bars.
Okay. Can you...
Is it possible for you to turn off your videos? That
or,
might aid
or maybe
your
just
audio.
type. Yeah, or maybe just type it in if that would be faster.
I think he's
Can you hear me now?
Yes, sir.
Sorry, I'm using my phone and
The audio is better now. Please go on. Can you switch? You can turn off your video to ensure the quality of your audio gets better.
Hello.
Yeah, go ahead, sir.
Hello, can you hear me? Can you hear me now?
We can hear you, sir. Go ahead, please.
But me, I'm really struggling to hear you out.
Let me just type a message to him. I could drop my email, so if there's anything specific here.
Okay, that's great. Ladi, please.
Okay.
Hello.
Shall I carry on? Can everybody hear me?
Yes,
yes,
can,
please,
Ladi.
please go on.
Okay. Dr.
Hello, can you hear me?
Ladi, I think you should just carry on. I think you're muted, Ladi.
I think it was a bit to control the guy from speaking.
Yes,
as well.
yes.
Okay.
Ladi, please, come on.
All right. Dr. Kaltungo, thank you very much for delivering this month's technical session titled Managing Failures in energy systems? Are we masters or slaves of data? I'm sure after today's technical session, we all have better understanding of elements such as data, data optimization, integration of maintenance strategies, and main reasons for failures. So please, everyone, join me in giving Dr. Kaltungo a round of applause for a well-delivered technical session today and a job very well done. Thank you very much.
Thank you. Thank you. Thank you very much. Thank you.
Buddy, you are seeing in we are now in digital age. We don't do physical clap. We do digital clap.
Remember, we said in maintenance strategy, everything works. So we have to combine. We have to combine all.
Even our Ferdinand is giving the digital clap.
The baby of the house.
Thank you very much, Daddy, for that.
No problem.
So let's we move straight away to general. But Patrick, before we do that, can you check whether Engineer Gutala is back on the call so that we can give her a moment to address us in her capacity?
She's actually on. She's on.
Please, because we.
Okay, I've asked her to unmute.
Hello, everyone. I'm so
Hi.
sorry. I just came back from Abuja and I was trying to do one or two things. So I went off for a while. But I did listen to the lecture. And I would say Dr. Akilu did justice to that paper. Maintenance is the bane of our lives in Nigeria. And once we are able to pay more attention to maintenance, I'm sure a lot of our facilities and our infrastructure will last longer. And then we'll be able to save costs as engineers too. And then, of course, it will also help us to focus more on more things and better infrastructure. So I congratulate Dr. Akilu for that wonderful lecture. And I congratulate Manchester branch for bringing this very knowledgeable man, to give us an insightful lecture. Getting all this done, getting knowledgeable people to deliver lectures is actually not a very small task at all. Having been a branch chairman myself, although at a time when things were not so easy, because Zoom makes you have more participants actually.
True.
So you get to have more participants listen, participate, and all that. It's a lot better now. It's one of the take home and one of the advantages, if I may say, of coronavirus. So it's not all bad. There's some good has come out of COVID-19. So I thank you for the opportunity to speak to you, and I look forward to many more of such wonderful and insightful lectures. Thank you.
Thank you so much, man. Thank you so much, man.
Yes, sir.
Engineer Kade, can you pull up our last minutes, or should I just depend